Hi, everyone. So today we are going to go ahead and pick up where we left off yesterday, and we don't have any notes to go through before we start jumping in with the in-class practice problems. So we're going to go ahead and just get started. So in this question, we are asked about a 5 kilogram rock that is sitting on a scale on the floor of an elevator. Okay. So when we're looking at an elevator, we need to draw the free body diagram first. And we talked about this yesterday a little bit. But when we're on an elevator, we have, and I'm going to draw it over here on the left, we have our elevator sitting, and the rock is sitting on a scale. Okay. And so there's the scale and there's the floor of the elevator. Now our rock is sitting right here. When we look at this, we need to think about what the forces are that exist on this rock. So first, we have the force of gravity that's going to be directed down towards the center of the earth. Then we have the normal force or the support force, and that's the force being exerted by the scale onto the rock. And that's the actual reading on the scale. So when we're looking at finding the reading on the scale, okay, we're looking at what is our normal force. Okay. And something that's really important to note is that your normal force, yes, it counterbalances the force due to gravity when you're dealing with something that's up and down forces and a normal force on a support like that, but it doesn't have to be. So your normal force is the surface force. It is the force being pushed out by the surface that the object is sitting on or where the force is being pushed onto. And we're going to look at different examples of that, but I just want you to know that the normal force does not have to be the same exact value as the value of the weight of an object. Okay. So now when we look at this question, it says a 5 kilogram rock is sitting on a scale on the floor of an elevator. If the elevator moves upward and speeds up at a rate of 2.3 meters per second squared. So in this case, I have my acceleration is going up, okay? And it's going up at a rate of 2.3 meters per second squared. Now, my rule of thumb for my elevator problems is that I'm always going to set the direction of my acceleration as the direction of my positive. I just feel like it's much easier to do the problems that way. So in this case, I'm going to look at my 2.3 as my positive, and I'm going to write my sum of my forces is equal to my mass times my acceleration. But my sum of my forces is also equal to actual forces. And those actual forces are my normal force, which is my upward force, minus my gravitational force, which is going to be in my negative direction. So I then end up having mass times acceleration is equal to normal force minus the force of gravity. So my normal force, which is what I'm solving for, is equal to my mass times acceleration plus my force of gravity. And my force of gravity is mass times gravity. So I end up having our 5 kilogram rock with an acceleration of 2.3 meters per second squared plus our 5 kilogram rock times 9.8 meters per second squared. Okay, and that's going to be the equation to figure out what the reading on the scale is. So when I add all of that up, I end up getting a value of 60.5. 60.5 newtons is what the reading on the scale is. Okay. Now, if you think about this, the reading on the scale, if it's just standing still, is going to be 5 times 9.8. So that's going to be close to 50. So you're going to have a higher reading on the scale as the floor is accelerating up towards your feet. Now, the elevator moves upward while slowing down at a rate of 2.3. So because it's slowing down, our velocity and our acceleration are in opposite signs. So our acceleration is downward at 2.3 meters per second squared. So the way I look at that is I can look at that as my sum of my forces is equal to mass times acceleration, and my sum of my forces is equal to, what's my downward value? My downward value is my weight, okay? So my force of gravity, or my weight, minus my normal force. So mass times acceleration is equal to mass times gravity minus my normal force, or my reading on my scale. So my normal force is equal to mass times gravity minus mass times acceleration. Okay. And when I go ahead and plug all of that in, I can actually go ahead and pull out my mass. So I have gravity minus acceleration times mass. So my mass is going to be 5 kilograms. My gravity is 9.8 meters per second squared. Okay. And the reason I'm able to use positive there is because I've set my downward as my positive. Okay. And then also I have times, or minus, I'm sorry, minus my 2.3. So I have 5 kilograms times 7.5. Okay. And that's going to end up giving me 37.5 newtons. Okay. Now the elevator moves downward while speeding up at a rate of 2.3. So moves downward while speeding up at a rate of 2.3. And the benefit for what I just did is I'm saying that it's speeding up going downward. So everything is going to look the exact same that it looked above. So it's the same as above. I end up getting my sum of forces equals mass times acceleration. And I also end up getting that my sum of forces is equal to mass times gravity minus normal force. So in that case, I end up getting that my normal force is equal to mass times gravity minus acceleration, which ends up giving me my same value of 37.5 newtons. Okay. Now you'll see a lot of different elevator problems. So you just need to make sure that you're drawing your free body diagram correctly. Okay. And that you're identifying what the location or the direction of your acceleration is when you're doing those elevator problems. Also recognizing that the reading on the scale is equal to the normal force. So our next question is our fisherman question. And this question is very similar to a question that you will do in your homework. A fisherman pulls a fish vertically out of the water with an acceleration of 2.5 meters per second squared while using very light fishing line that has a breaking strength of 22 newtons. So the whole idea there, so this breaking strength of 22 newtons, what does that mean? That means that if the tension is greater than or equal to 22 newtons, then it breaks. Okay, that's what that means. Okay, unfortunately, the line snaps under these conditions. What do you know about the mass of the fish? So if we look at our fish is sitting there, and I have a tension force going upward, and I have the mass times gravity of my fish going downward. So notice I just labeled that as mass times gravity, but that's the equivalent of our gravitational force, or also our weight. Okay. So if I look at this, my sum of my forces is equal to mass times acceleration. Something I have not done yet is I haven't identified or defined my acceleration. Well, I'm going to define my acceleration over to the left because I don't want to make the readers think that I believe that is included in the free body diagram. So I'm going to do it over here on the left, and I know my acceleration is going to be upward. So I'm going to make my upward positive. Sum of forces equals mass times acceleration. So my sum of forces is my upward minus my downward. So that's equal to my tension minus mass times gravity. So mass times acceleration is equal to tension minus mass times gravity. The tension in this case is equal to mass times acceleration minus mass times gravity. Okay? Now here's the deal. In this case, I want my tension to be at least 22 newtons. So I'm going to plug in 22 newtons here, and that's equal to my mass times my acceleration minus my gravity, which is 2.5 minus 9.8. Okay? Oh, if you look at that, this is actually plus, and this is plus. Okay? So 2.5 plus 9.8 equals 22 newtons. So if I divide both sides by that, I end up getting that the mass of my fish must be at least, it must be equal to or greater than 1.8 kilograms. Okay? So moving on to our next question, we have a question about an upward tension force pulling on an object with a force of 1/3 the object's weight. So we have an object and we have an upward force. This is our force of our pull. And then we have our weight going down. So our weight or our force of gravity. And so we know that the sum of our forces is equal to mass times acceleration. The sum of our forces is also equal to, okay, let's see, if we pull up, calculate the magnitude and direction of the object's acceleration. So let's say we set our upwards as positive. So we have force of the pull minus our weight, okay? So we have our mass times acceleration is equal to, our force of our pull is 1/3 our mass times gravity minus our mass times gravity. So what do you notice? We have mass, mass, and mass. Mass can cancel, which makes our life much easier. And therefore, we get that our acceleration is negative 2/3 gravity, which is 9.8. So it's going to be 6.6 meters per second squared downward. Okay. And that is the magnitude and the direction of our acceleration in that case. So in this next section, we're going to be looking at the applications of Newton's third law. Okay. So we need to have an understanding of what Newton's third law is. Newton's third law is basically our action-reaction type law. Okay. For every action, there is an equal and opposite reaction. So what does that mean? When you have two objects that are going to interact by exerting forces on each other, you're always going to have two forces that happen at the same exact time. One object applies a force onto a different object. That's the action force. The other object applies the same magnitude of force, but in the opposite direction on the first object. So for example, if I have block 1 and block 2, okay? Well, block 1 is applying a force on block 2. Block 2 is applying an equal and opposite force on block 1. So we have force of 1 on 2 is equal to the negative force of 2 on 1. Okay, and that's what you have here. If A on B, then that's equal to negative FB on A. So how does this apply to connected objects? Because that's the next thing that we're going to go into is this idea of connected objects. And we're going to look at 2 or 3 different problems on connected objects. Every internal force can be ignored because the forces are going to cancel. But the net external force for the overall system is equal to the mass times the acceleration. Okay, so we're going to take a look at some applications of Newton's third law. And here we have our connected objects. We have a 20 kilogram mass, an 8 kilogram mass, and a 30 kilogram mass, and they are being pulled. Okay, so we have 3 objects are connected as shown in the picture and are moving across a frictionless surface. If a 50 Newton horizontal force pulls the front block to the right, find the acceleration of the whole system. So when we look at this, we have a 50 Newton pulling force. Okay, and then we have different tension forces. So in this tension, the tension here, we have a tension of, and that's tension of 3 on 2. Okay, so we'll call that tension 3 on 2. And then we have a tension this way, which is tension 2 on 3. Okay, now if you look at the next string, we have our tension 1 on 2. And then we have a tension of 2 on 1. So what does that tell us? Well, it tells us that these can't, so if we look at all of the sum of forces, okay, I could do it on the diagram, but I'm going to do it down here. Force equals mass times acceleration. So the sum of forces for the entire system, well, we have 50 newtons to the right. And then we have minus the force or the tension 3 on 2 plus the tension 2 on 3 minus the tension 2 on 1 plus the tension 1 on 2. And Newton's third law tells us that 3 on 2 is the same as 2 on 1. So those are going to end up canceling. And the same with these ones are going to end up canceling. So our overall force is equal to the mass of the entire system times the acceleration. And that's equal to 50 newtons. Okay, so we end up getting that the masses, so we have 20 plus 30 plus 8, so we have 58A is equal to 50 newtons. When I divide both sides by 58, I end up getting that the acceleration of the entire system is 0.86 meters per second squared. Now, that means that block 1 is accelerating at 0.86 meters per second squared. Block 2 is accelerating at 0.86 meters per second squared. And block 3 is accelerating at 0.86 meters per second squared. And we know that they are accelerating to the right because we've set our right as positive in this case. Okay? Now, we're going to zoom in for a second. So that's zooming out at our whole system. But then it says, now find the tension in the cord connecting the front 2 blocks. So now I want to focus specifically on the forces that are acting on 3. So I have the tension of 2 on 3. So I actually drew that backwards above. Okay. And then I also have our 50 Newton force. Okay. And we know that the acceleration is 0.86. So we have the sum of forces equals mass times acceleration. The sum of forces is equal to 50 minus the tension. Okay, so we have mass times acceleration is equal to 50 minus tension, because I'm combining this sum of forces and that sum of forces. Okay, so I end up getting that my tension is equal to 50 minus my mass times acceleration. So minus 30, because I'm looking at the mass of just mass 3. So 30 times 0.86. And so that ends up giving me 24.2 newtons. Okay, it's very important that you keep your work nice, neat, and organized, and that it's easy to follow. Okay, question number 10. This is what we call an Atwood device, and basically we're looking at two objects that are connected through pulleys, or any number of objects connected through pulleys. It says two objects are connected by a light string that runs over a lightweight pulley. So we have our pulley here, and we have a thin piece of rope, and we have two objects, or two boxes. Okay. The frictionless pulley, such as the objects, hang freely. If the two objects have a mass of 5 kilograms and 8 kilograms, so this one is 5 and this one is 8, find the acceleration of the system. So if you think about this practically, which one is going to move down? And the way I look at that is which one is going to pull more on its side? Which one has a stronger force pulling? And the force of gravity on 8 is going to be much stronger. So I know that my acceleration is going to go this way. So this block is going to accelerate that way. This block is going to accelerate that way. Okay. So now I want to draw my free body diagram for each. My free body diagram here is going to be equal to my tension. And then I have force of gravity, or my weight, 5. Now over here, I have my tension. And then I have my weight for object 8. Okay. So what's really important is to note that I drew, or tried to draw, my weight for 8 much longer, and my two tensions are actually equal to each other, because when two objects are connected by one string, the tension in that string is the same throughout unless otherwise stated. So there are actually two different ways to look at this problem. The first way to look at this problem is we can find the sum of the forces on object 8, which is the mass of 8 times acceleration. And then we have the sum of forces is equal. So the sum of forces on object 8 going in the direction of the acceleration is weight 8. So mass 8 times acceleration due to gravity times g minus tension. The sum of forces on our object 5 is equal to mass 5 times acceleration. And those forces are equal to, so tension is now going in the positive because I've set my acceleration as positive. So tension minus mass 5 times g. So I end up having 8a equals 8g minus tension. And 5a equals tension minus 5g. So I'm going to go ahead and solve for tension here. Okay. When I solve for tension in this equation, I get tension equals 5a plus 5g. And then I'm going to use substitution and move that over here. Okay. So I get 8a equals 8g minus 5a minus 5g. The reason it's minus is because I need to make sure that I don't forget to distribute my negative charge there, or my negative value there. Okay. So in this case, I now end up resituating everything. So I get 13a is equal to 3g. And then I end up getting A is equal to 2.26 meters per second squared. Okay. Now that's the first method to do these problems. Another method, because they're both connected by the same block, we can look at the mass of the entire system. Okay. So we have two different methods. This is method 1, and this is method 2. Okay, so in our whole system, the mass of the entire system is 13 kilograms. Okay, and going to the right, we have the mass of 8 times gravity. So we have the weight of 8. Going to the left, we have the weight of the 5 kilogram block. Okay, if we were to combine this as if we're looking at the whole system, the system as a whole, and we know that acceleration is going to end up going this direction. So we know that the sum of forces is equal to mass times acceleration. The sum of forces is also equal to weight A minus weight 5. So when I substitute here for my sum of forces, I get my mass A is equal to 8g minus 5g. So I end up getting 13A equals 8g minus 5g, which is 3g. So then in that case, I end up getting 2.26 meters per second squared. So you'll notice I get the same exact answer both ways, okay? But you have to pick the way that conceptually makes the most sense to you, okay, when you're doing that problem. Now, this one is a significantly more challenging Atwood device problem. We have 3 blocks are connected with a lightweight string and hung over pulleys at opposite sides of the table, as shown in the diagram. If the table is frictionless, that's super important for us to recognize. It's frictionless. How fast does the 9 kilogram block accelerate when it's released from rest? So we have to look at all of our systems. Well, look at our free body diagrams. Here we have our tension, and I'm going to call this tension 1. And we have our weight of our 9 kilogram block. Up here, we have our normal force, and we have our weight of our 5 kilogram block. We then have our tension 1, and then I'm going to call this other one tension 2. Now over here, I have tension 2, and I have my weight of object 2. And I'm going to go ahead and pick my direction of acceleration, because if I get a negative value, that just tells me that my acceleration is the other direction. So I'm going to assume that my acceleration is going to happen this way. So my acceleration is going to happen clockwise. Okay. So now I have to look at my sum of my forces. So I'm going to have my sum of forces on my 9 kilogram block. It's a 9, not a G. Is equal to mass times acceleration. The sum of forces on my 9 kilogram block are equal to, if I'm setting my acceleration as down, I have 9g, so my weight of my 9 kilogram block minus tension 1. So I have 9a equals 9g minus tension 1. Then I'm going to move to my next block, my 5 kilogram block. My 5 kilogram block is mass 5, acceleration, and the sum of that force is equal to my tension 1 minus my tension 2. So I end up getting 5a equals tension 1 minus tension 2. Okay, and then my sum of my forces on my 2 kilogram block is mass 2 times acceleration, which is equal to my sum of my forces. So I'm going to also look at my sum of forces. On that one equals tension 2 minus mass 2 times gravity. So I end up getting 2A equals tension 2 minus 2G. Okay, so now I have 3 equations, but I have 2 unknowns. So I need to start solving for things. Okay, if I look at this, why don't I start solving for, I'll look at this equation in the center and I'll solve for T2. So T2 is equal to T1 minus 5A. And now I'm going to take that and I'm going to substitute T2 in down here. So now I get 2A equals T1 minus 5A minus 2G. So I end up getting 7A plus 2G equals T1. And now I'm going to go and substitute that all the way up here. Okay, so then I get, so I'm going to take this and I'm going to move it over here. 9A equals 9G minus T1. So minus 7A minus 2G. Okay, so I end up getting 7G is equal to 16A. Acceleration is equal to 7 times 9.8 divided by 16. And so I end up getting that my value is going to be 4.3 meters per second squared. And that is the rate at which it's accelerating. Now, a question like this, you could solve so many different questions, okay? So many different questions. And so it's really important to be able to break down the problem into our components. Now notice I didn't say anything about our x, y components, but if you look here, my normal force, the only components, you need to look at the components that are going to affect each other. So for block 9, it's the y components that affect each other or they affect the motion. For block 2, it's the y components that affect the motion. But for block 5, it's the x components that affect the direction. But we can still use substitution in this. So this is something that you got to practice and practice and practice. And when you don't understand and you get it wrong, you reach out and you practice until finally, all of a sudden, it starts to make sense. And it could take someone days, it could take someone weeks. Okay. But the most important thing is that eventually we end up figuring out what we need to do.